Hi everyone, my name is BehzadAkbari, and I'd like to start by telling you a little bit about myself. I completed my PhD in ECE department at McMaster University in 2021 after earning my master's degree in computer science department, same university. My main area of research has been target tracking and sensor fusion and AI. I have over 10 years of teaching experience starting back in Iran. And also last year, I had the opportunity to teach 7 different courses at Nipissing University Computer Science Department in North Bay, Ontario. These courses include digital systems, computer architecture, distributed systems, and AI. Um, and it was a great experience that allowed me to connect with students from diverse background, learning style in Canada. But today, I'm excited to share with you guys one of my favorite topic in digital system design course called Optimizing Digital Circuits using KarnoMap. This is a powerful and practical tool, and I hope you will find it interesting as I do. Let's get started. In this course, before talking about KarnoMap, in previous sessions, we learned some um, information about circuits. We know that normal circuits, that we call them combinational circuits, have some inputs and outputs. And um, we can summarize connection between input and output in a table called truth table. We already know that. And a truth table shows all possible input combination and their corresponding output. And we also know from truth table, we can find actually a Boolean expressions for each output based off these input Boolean variables. For example, imagine we have an aircraft wheel monitoring system that we have 3 inputs for landing gear sensors and 2 output uh, that are 2 LED outputs, red and green, that's showing if, for example, landing gears are extended properly or one of them retracted. Um, for this system, um, to write, for example, to find the output, for example, for red LED, we need to look at the rows where the output are 1. Like here we have O1, as you can see. So we need to look at these ones and identify the corresponding minterms and combine them using OR operations. Okay, so we know already that, like for this system, the corresponding actually Boolean expression for red LED is this operation that, as you can see, is quite large. And designing the circuit for that is very bulky and inefficient. Can we make it um, more efficient? Can we make it simpler? Yes, we can. It's possible to use Boolean algebra to do that, but Boolean algebra is not a systematic way and it's hard to implement it with like algorithms. This is where KarnoMap come in. A KarnoMap provides a systematic way for actually simplify Boolean expressions in form of minterms, like what you can see in this example. Let's see how that works. The Carnot map was invented in 1953 by Maurice Carnot, an American actually computer scientist. The Carnot map is a grid of squares or a matrix of squares together. And each square represents a minterm, as you can see in this picture. So a Carnot map structure summarized um, through table as well. So the total number of squares is 2 power n, if n is the number of inputs. And we fill these squares with 0 and 1 like through table. And the cool part about kernel map is that adjacent squares or neighbor squares differ by the value of just one variable. The reason is that these codes here 0, 0, 0, 1, 1, 1, and 1, 0 are not binary codes. They are gray code, and gray code has this characteristic that they are different in just one variable, and that helps us to can eliminate this variable. So for example, imagine um, we have these expressions. X has 4 minterms, so corresponding kernel map structure for that is like that. How we can group them and how we can shrink them, we're going to see in this next. First is the grouping part. Grouping part is very challenging part and is a process of combining squares with ones to simplify a Boolean expression. Grouping has some rules. First of all, they need to be power of 2. So we can group 2, we can group 4 squares, we can group 8, but we cannot group 6 squares. And groups should be as big as possible. Larger group means simpler expression. Also, another good actually uh, rule about groups are that groups can be wrap around. Like for example, um, group group in here, squares in here and here are also considered neighbors. So if there is one here and one here, we can group them together. That's called wrap around um, squares. So how we can find uh, the shrink term or group term? We just need to look at the group and find all the variables that are common across the entire group. Let us see one example. Like in this example, imagine um, um, we want to group. So can we group these two? Yes, we can. Um, this can we make it bigger? No, it's not possible. What about this? Can we group this? Yes, we can. So actually overlapping two groups is possible. That's important. What about this? Can we group this with any other one? No. So this is one. So how we can find the group term? Group term for this, for example, is the variables that are in common. What is in common? A is in common. No. B is in common. Yes. C bar is also in common. So this is how we find the group term. Let have let's go back to the previous example that we had, aircraft wheel monitoring system. As we said, in this system, we have 3 input and 2 outputs. So we can find the truth table. We already explained that. Based off this truth table, we can write actually a kernel map. Kernel map for 3 variables is like that. Um, this kernel map is for red LED. How we can write that? Oh, here is 0 because 0, 0, 0 is 0 and the rest are 1. So how we can group that? That's the important part. Can we group these 6 elements, these six squares? No, because 6 is not power of 2. What about this 4? Can we do this? Yes, we can. So we can group this 4. What about this? Can we group this 2? Yes, we can, but it's not optimal. Can we make it 4? Yes, overlapping is allowed. So we can overlap these 2 and make 4. What about this? Can we make this just 1? Yes, but it's not optimal. We can make this grouped all together. What about just makes these all 4 squares together? So this is grouping. So the final group's gonna be like that. After grouping, we need to find the summarized variable. For red, the common variable is C. For green, the common variable, as you can see, is just B. And for blue is only 1. And the result is actually A plus B plus C. So just with 1 or A, B, and C instead of that bulky um, um, circuit, we can make red LED. circuit. Thank you so much. And this was my presentation.